VLSos here. This is a video lesson on the area between two curves. Let me make a sketch of what we mean by that. I'm going to make a simple graph of one function we'll call f and another function or curve we could label g. What we mean by the area between two curves is the area that is surrounded by two functions. We need to know where those functions intersect. The area between these two curves begins here and is the region that I could shade and then ends here. The two locations which the functions are equal become the bounds of integration. We're going to set up an integral to find this area. Those bounds, a and b, need to be found, and they will be the values where the functions are equal to each other. When you have a problem with the area between two curves, sometimes you'll need to do the algebra to find where those functions are equal so you know what your bounds of integration are. And once you have them, a definite integral from a to b can be used to calculate the area between those two curves. And the strategy is this. If we find the area under the curve of the function that is on the top, and in this case, f is on the top on the interval in which we're integrating, and we find that larger area and subtract the area under the curve of the bottom function, then we'll get the difference between those two areas. The large area minus the smaller area under g will leave the area between the two curves, which has been shaded. So the definite integral from a to b of f with respect to x is the area of the top function, the area under the curve of the top function. And we're going to subtract the integral on the same bounds from a to b of the bottom function to find the smaller area, and the difference is the area between the curves. We can use an integral property, in this case, to write it as one single definite integral. Because the bounds are the same, we can make a difference of the functions on the integrand and put them into one integral. It is not necessary to do this when you're working an actual problem. It depends on what you need and what is easier to integrate, whether you separate it out or you combine it and integrate once. Depends on the situation. Let's provide a concrete example. I'm going to define the function f as the line x minus 1 and the function g as the cubic function x cubed minus 2x squared plus 1. And I'm going to graph them to get an idea of the region or the area between f and g that we're going to calculate. The line x minus 1 is simple to graph. That's f. G is a cubic function. We could use a t-table, plot some points or some technology. Its graph looks like this. And it curves to a minimum and then back up. The area between f and g is more sophisticated than our first approach where we talked about the concept, because the area between these two curves has two distinct and separate regions. And the region here, which is a little bit larger than this sliver, has a portion that is below the x-axis, and we're used to thinking that is a negative amount of area, or an area that represents a negative sum if it's below the horizontal axis. So let's think a little bit about what it means to use an integral to find the difference between the two areas. An integral, remember, is a sum. What we're adding is we're adding infinitely thin rectangles. To get an area under the curve is literally the sum of a whole bunch of lines. So to find the sum of an area between two curves, we're finding the sum of the difference between two values that then produces those infinitely thin lines. And whenever we have a length that we're summing up, then the sum is always going to be positive. Again, in this example here, where we have sum below the x-axis, we're going to disregard that we have a region below the x-axis. We are not going to count it as negative, because when we find the difference between f and g, no matter where g and f points are, they're always going to produce a positive value, which represents the length of the line that connects those two values. So the area between two curves is always positive. Let's do that calculation. We need to find where f and g are equal to each other. So if we set the f function equal to the g function and solve for x, we will get the locations of these intersections. This requires some algebra. The algebra has been done, and the result is that the x locations of the intersections are -1, 1, and 2. And it looks that way from our graph, but we can't trust that a graph is going to tell us where those precise locations are. We have to do the algebra to get those results. So from -1 to 1, that is the region that is bounded between these 2 points. And the function that is on top is g, and the function on bottom in this region is f. So we set up the integral. The integral from -1 to 1 of the g function minus the f function, top minus bottom, with respects to x. And then we're going to add this region here, which requires its own integral from 1 to 2 of the top function, in this case f, minus the bottom function g. These two integrals cannot be combined into one because the bounds of integration are different intervals. But we can substitute the functions in this case, the g function, or the integral from -1 to 1 of x cubed minus 2x squared plus 1. And then we're going to subtract, we're using parentheses because we would need to distribute a negative, we're going to subtract the f function x minus 1 with respects to x. And then we're going to add the other integral, in this case, the integral from 1 to 2 of the f function, x minus 1, and then we're going to subtract the g function, which should be put in parentheses because we'll need to distribute a negative with respects to x. This integral, the sum of these two integrals, if you use technology or techniques, we're not going to do it here, but it will produce the area between those two curves.